Hello, calculus students. Well, today I want to talk about the proof of the chain rule. And this is fairly complicated, but if you take your time and pause the video where you're not sure and look at what I'm doing, I explain this in a way that I hope everybody will understand it. And the reason I do this, even though it's kind of complicated, is I hate it when people say, here, memorize this, without explaining why. If you go through this slowly and understand why this is true, then it's so much easier to use. It's hard to memorize something when you don't believe it, but hopefully you'll believe the chain rule after I go through this proof. Again, this is optional. You don't have to go through this, but this I think helps to learn it when you know what it is. Okay, so we start out with the chain rule is about taking the derivative of the composition of a function. So if we have functions that are in composition and we want to take the derivative of that. So if we have y equals the fog of x, in other words, y equals f of g of x, we want dy dx. Okay, so this is what we want. So first of all, let's go back to our old standard. You probably dream about this. You should be dreaming about it. If you're not dreaming about math, you're not doing enough work on math because it sticks in your subconscious and it comes up in your dreams. But you've done a lot of work with derivatives. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. All right, so now we have to do this one like that. So now when we do this, we have f of g of x plus h. Instead of x plus h here, we have a g of x, so this is g of x plus h. And instead of a minus f of x, we have a minus g of x. And it's all over h. So I hope you're okay with that. All right. Now, whoever came up with this proof was a genius. And it's amazing how a lot of times you don't have enough pieces to be able to prove something, but you can add pieces to it if you use the right pieces, and a lot of times in proofs you'll multiply by 1. You get a special 1, you multiply it by it, or you might add a 0, a special 0. And I'll show you what I mean by a special 1. If we have, say, x equals 2, if I multiply the top and bottom of x by 7 over 7 times x, this isn't changing anything. I'm multiplying by 7 over 7. I'm multiplying by 1. Nothing changes here. In fact, when we add fractions with different denominators, we do that. We multiply the top and bottom, the numerator and denominator by a number to get the lowest common denominator, and that's just a 1. So if I multiply something by x squared plus 3x minus 11 all over x squared plus 3x minus 11, if I multiply something by this, didn't change it. It's just 1. All right, so what we're going to do is we're going to use g of x plus h minus g of x all over g of x plus h minus g of x. And someone thought hard to come up with this 1, because this is what we need to prove this. So this is just 1. If I multiply by this, it doesn't change anything. So here it is, right here. Here's my 1. So I've got this, and now I just put this inside the limit. This is 1. Nothing's changed here. All right. So now let's take a look at another interesting fact, and that is if we have 3/7 times 4/5, if I want to multiply these fractions, I multiply the numerators together, I multiply the denominators together, I get 3 times 4 over 7 times 5. Now, with commutative property, 7 times 5 is the same as 5 times 7. So I can switch these if I want and say this is 3 times 4 all over 5 times 7. Okay, so I can split that back into fractions and say this is 3/5 times 4/7. So it's kind of interesting. 3/7 times 4/5 is the same as 3/5 times 4/7. So we can switch these denominators and it doesn't change anything. Right, so this is what we do here. We take on this step right here and we take and we just switch these two denominators. We're multiplying, so I switch these denominators. This came over here and the h went over there. All right, again, stop at any point and look at it, make sure everything makes sense. Now, if you have the limit of a product, here we have the limit of a product, that's equal to the product of the limits. Remember going back, it's a few chapters back when we talked to limits, but if we take the limit of a product, it's the product of the limits. So I can take and split this up into two limits. Take this, put this limit in here, and I have two limits. This only works if both these limits happen to exist, and in this case, they do. All right, so now we're at this step here, and notice, take a look at this. The limit as h goes to 0 of g of x plus h minus g of x over h, that's just our derivative. This is f prime of x. This is just g prime of x. So here it is. Right there, g prime of x. So now we finally got that this is equal to the limit as h goes to 0 of f of g of x plus h minus f of g of x all over g of x plus h minus g of x times the derivative of g of x. Now we've got to do some work with this. All right, so let's see if we can clean this up and make this actually work. So we're going to start by letting g of x plus h minus g of x equals k. Because if we had a k down here, like an h, and we could send k to 0, that would work a lot better. So we're just going to say that. Now, if we take the limit of g of x plus h minus g of x as h goes to 0, this h goes away. We have g of x minus g of x. This is just 0. At the same time, this is also k. So we see the limit as h goes to 0 is the same as the limit as k goes to 0. As this goes to 0, k is going to 0. All right, so I want to rewrite this using this. Well, here's my g of x plus h. Here's g of x plus h minus g of x plus h minus g of x equals k. So let's solve for g of x plus h. Let's take this and solve that. So this is g of x plus h. All I do is add a g of x to both sides, and I get g of x plus k. Just simple algebra, just move that over to the other side, and I have that. So now let's just change this to this. Okay, so now I have dy dx equals the limit, and now I'm looking as k goes to 0 of, so I'm replacing this with this. So I have f of, instead of g of x plus h, I've got this, g of x plus k minus, and now I have f of g of x, nothing changed here, and I've got this all over k. All right, so let's go back to this. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, we know this is true. And now instead of an x, instead of f of x, we've got a g of x here. And instead of x here, we have a g of x. Now we're using k in this case instead of h. But notice, this is the derivative of f of g of x. This is f prime of g of x. just if you replace the g of x with an x, you can see that. All right, so that's what this is right here. So this and this limit here are the same. So now dy dx equals f prime of g of x times g prime of x. So that is a proof of the chain rule. You take the derivative of a function, and all you do is take the derivative of this function and then take the times the derivative of the inside function. Now with the power rule, the general power rule is just this is just part of the chain rule. I mean, this is just a simpler part of the chain rule. If we have say we have f of x to the nth power, and we want d dx of this, well, we have to take the derivative of this, which is just n times f of x to the n minus 1, and then we have to take the derivative of the inside, which is times f prime of x. So by proving the chain rule here, we've proved this. This is a special case of the chain rule. All right, I hope you believe now in the chain rule. I hope you believe this is true. See you in the next video.